There is a line in space, not a comet trail, not a satellite streak, a straight line of stars, nearly 200,000 light years long, stretching across the void like someone drew it with a ruler. For scale, that is almost twice the width of our entire Milky Way galaxy. When astronomers first spotted it in Hubble Space Telescope data, nobody believed it was real. Lines don't happen in space. Galaxies are spirals, ellipses, chaotic collections of stars, pulled by gravity in every direction. Straight lines are not supposed to exist. But this one did, and the explanation behind it would turn out to be stranger than anything the researchers had guessed. Somewhere out there, a black hole with the mass of billions of suns is running for its life through the emptiness of intergalactic space, and it is leaving a trail of newborn stars in its wake. The story begins with a routine observation. Astronomers were combing through Hubble imaging, cataloging distant galaxies, when a strange linear feature caught their attention. It wasn't attached to any obvious galactic structure. It didn't curve, it didn't spiral, it simply extended, straight and thin, glowing with the unmistakable blue light of young, hot stars. Blue light matters here. Stars burn different colors depending on their age and temperature. Older stars tend to glow red or orange, cooling gently over billions of years. Young stars burn hot and blue, blazing with the kind of energy only fresh nuclear fusion can produce. So this line wasn't an ancient structure left over from the early universe. It was young. Astronomically speaking, some of it was possibly only a few million years old, a blink of an eye compared to the 13.8 billion year age of the cosmos. That raised an obvious question. What could organize millions of stars into a single straight line, stretching across a distance so large it would take light 200,000 years just to travel from one end to the other? Scientists don't jump to the most dramatic explanation first. They work through the possibilities methodically, testing each one against the evidence until only one survives. The first theory was simple. Maybe this was just a thin, edge-on galaxy. Seen from the right angle, a spiral galaxy can appear as a narrow streak of light, but the structure didn't behave like a galaxy. It lacked the mass distribution, the central bulge, the gravitational signatures that hold a galaxy together. It was too uniform, too narrow, and too isolated. The second theory involved radio jets, some supermassive black holes, particularly active ones feeding on surrounding material, launch enormous jets of charged particles at nearly the speed of light. These jets can, in rare cases, compress gas and trigger star formation along their length. It seemed plausible. Radio jets are known to sculpt their surroundings across galactic scales. But when researchers checked for the telltale radio emission that accompanies an active jet, they found nothing. No radio signature, no evidence of the kind of energetic particle acceleration a jet would produce. The jet theory collapsed. That left the astronomers with a straight line of young stars tethered to a distant galaxy at one end, with no galaxy shape, no jet signature, and no conventional explanation. Something else was going on. And to figure out what, they needed a more powerful set of eyes. Enter the James Webb Space Telescope. Where Hubble captures visible and ultraviolet light, Webb specializes in infrared, allowing it to see through dust, resolve fainter details, and detect the subtle signatures of what's actually happening inside cosmic structures like this one. When Webb turned its instruments toward the linear feature, the picture sharpened dramatically. At one end of the trail sat a compact, extremely bright, high-energy source. Spectroscopic analysis, essentially breaking the light down into its component wavelengths, revealed something extraordinary. That bright point wasn't a star. It was the unmistakable signature of a supermassive black hole, actively feeding on surrounding gas and moving through space at a staggering velocity of nearly 1,000 kilometers per second. To put that number in perspective, at that speed, you could travel from Los Angeles to New York in about 4 seconds. This is a black hole containing the mass of hundreds of millions of suns hurtling through intergalactic space fast enough to escape the gravitational grip of an entire galaxy. It is not sitting quietly at a galactic center the way most supermassive black holes do. It is running. Here is where the discovery becomes genuinely mind-bending. The black hole itself isn't creating stars directly. Black holes don't manufacture matter. Instead, it is acting like a snowplow, moving through a field of thin, invisible gas that fills the space between galaxies. As the black hole races forward, it slams into this ambient gas, generating a bow shock. Think of the wake a speedboat carves through water, or the shock wave a jet fighter produces, breaking the sound barrier. That shock compresses the gas immediately ahead of and around the black hole's path, squeezing it far more densely than it would naturally sit in the sparse environment of intergalactic space. Compressed gas cools rapidly, and cool, dense gas is exactly the ingredient needed to trigger gravitational collapse, the process that gives birth to stars. As the black hole plows onward, it leaves behind a continuous trail of compressed, cooling gas clouds, and within those clouds, gravity takes over. Pockets collapse, ignite, and become new stars. The result is a 200,000 light-year-long stellar nursery stretched out behind a fleeing black hole like sparks trailing a comet. Millions of stars born not because the black hole made them, but because the black hole created the exact physical conditions necessary for star formation to occur, one shockwave at a time. This is the first time astronomers have observed this process happening in such clean, dramatic fashion. It transforms our understanding of what a rogue black hole can actually do to its environment. Rather than being a destructive void that only consumes, this one is inadvertently constructing new stars. So how does a black hole end up ejected from its own galaxy in the first place? The leading explanation traces back to an extraordinarily rare cosmic event, nicknamed the Cosmic Owl, a collision between two ring galaxies. Ring galaxies themselves are unusual, typically formed when one galaxy punches directly through the center of another, creating a shock wave that pushes gas and stars outward into a ring shape, similar to the ripple from a stone dropped in water. When two such galaxies merge, their central supermassive black holes are drawn together by gravity over millions of years, eventually spiraling inward and colliding. When two black holes merge, the collision releases an almost incomprehensible burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself. Under most circumstances, this energy radiates outward symmetrically. But if the merging black holes have different masses or spins, the emission becomes asymmetric. Gravitational waves are released more strongly in one direction than the other. That asymmetry acts like a rocket engine. By the same principle that pushes a rocket forward when it expels exhaust in one direction, the newly merged black hole receives a powerful recoil kick in the opposite direction of the strongest gravitational wave emission. In extreme cases, that kick can reach thousands of kilometers per second, more than enough to overcome the gravitational pull of an entire galaxy and send the black hole flying into intergalactic space. This is almost certainly what happened here. Two galaxies collided, their black holes merged. The recoil kick fired the newly combined black hole out of its home galaxy entirely, and it has been racing through the cosmos ever since, compressing gas and forging new stars every step of the way. For decades, the recoil kick was a theoretical prediction, something general relativity allowed mathematically, but that had never been directly observed in action. This trail of stars is the first clear physical evidence that supermassive black holes really can be violently ejected from their host galaxies. That single confirmation opens up a much larger set of questions. If one runaway black hole exists and left behind a visible trail, how many others are out there, drifting silently through intergalactic space without any obvious signature to give them away? Some estimates suggest recoiling black holes could be far more common than previously assumed, simply because most of them wouldn't be plowing through dense enough gas to create a visible trail like this one. It also reshapes how astronomers think about star formation on a cosmic scale. Star formation has traditionally been understood as something that happens inside galaxies fueled by galactic gas reservoirs. This discovery shows that rogue black holes, entirely detached from any galaxy, can independently trigger the birth of new stars simply by moving through diffuse intergalactic gas. That is an entirely new mechanism for building stellar populations, one that doesn't require a galaxy at all. Looking forward, astronomers are hopeful that upcoming observatories, combined with machine learning search algorithms capable of scanning enormous survey datasets for similar linear features, will uncover more of these runaway black holes. Each one found would refine our understanding of galaxy mergers, gravitational wave, recoil, and the surprisingly productive relationship between destruction and creation on a cosmic scale. A black hole capable of swallowing light itself is, in this case, responsible for building an entire trail of new stars simply by running away. It is a reminder that the universe rarely behaves the way intuition suggests, and that some of the most important discoveries begin with astronomers noticing something as simple as a line that shouldn't exist. If this kind of discovery fascinates you, the kind of find that rewrites what we thought we understood about galaxies, black holes, and the forces shaping our universe, make sure you are subscribed, because this channel breaks down stories like this one every day. Drop a comment and let me know. Do you think runaway black holes like this one are common throughout the universe? Or is this a rare cosmic accident we got lucky enough to catch? And if you want to understand exactly how gravitational waves can kick an object the mass of billions of suns across a galaxy, stay tuned, because that is exactly what we are unpacking next.